Hello, Chem 151 lecture. We are in week 10 of our 15-week experience in general chemistry and effectively week 1 of our online experience. Anyways, today we are going to discuss the quantum mechanical model of the atom. Now, to start off, essentially the periodic table can be looked at as different blocks of elements, and these blocks are relevant to better understanding how electrons actually work. And for elements in the first two groups, and with helium added to that, those would be the S block elements. The other main group elements in groups 13 through 18 would be P block. Those cool transition metals in the center would be D block elements. And then the guys that are often put to the side, the lanthanides and the actinides, are the F block elements. Something to note about the F block elements is that for the lanthanides, they are actually part of period 6, and the actinides are actually part of period 7, but they're kind of separated and moved downward just so that the entire periodic table can be fit onto one screen. But anyways, we're normally, for what we've done in the past where the group number was important, today the period number is actually what's going to be more relevant. Now, electrons, we've already, at the beginning of the semester, we did Lewis dot structures, which was a way of representing the outermost electrons, or the valence electrons. And these guys, well, it's cool. Lewis dot structures, they kind of sometimes give the wrong impression that electrons exist in infinitesimally small points in space. In reality, quantum mechanics says that electrons really have properties of both matter and waves, and therefore they're not really in distinct points, they're in distinct points in space. Really, they occupy regions of space, and those regions of space, according to quantum mechanics, would be called an orbital. Now, in order to describe the electrons in an atom, each individual electron, whether it is the outermost valence electrons or even the internal electrons, each electron has its own set of 4 quantum numbers, which would be the principal, the angular momentum, the magnetic, and the electron spin quantum numbers. These quantum numbers are used to help distinguish the different electrons in an atom. And according to the Pauli exclusion principle, in a particular atom, each electron has a unique set of quantum numbers. Now, starting off with the first quantum number, that would be the quantum number, the principal quantum number, which is symbolized with the letter N. And essentially, these describe the energy level the electron is at. Now, as you get further and further away from the nucleus, those electrons are naturally at higher energy levels. And so the value of N is essentially a whole number. It could be 1, 2, 3, etc. Now for S electrons and P electrons, the principal quantum number N is going to equal the period number. Now for D electrons, the principal quantum number is going to equal the period number minus 1. Whereas for F electrons, the period number minus 2 would be the principal quantum number. So for something that's in the second period of the periodic table, an S element, its outermost electron would be in the second energy level. Now take something like an element in the fourth period that's also a D block, whereas in the fourth period, an S block element or a P block element, its outermost electron would be in the fourth energy level or the fourth principal quantum number. A D block element in the fourth period would actually be in the third level, so 4 minus 1. And that's how that stuff works. The angular momentum quantum number which is represented by the symbol L, that describes the shell of a set of orbitals the electron is located in. And the different sets are essentially S, P, D, and F. Now, for an S electron, the angular momentum number will always equal 0. For a P electron, L would equal 1. For a D electron, L would equal 2. And for an F electron, L would equal 3. So as some practice, just to work with, if you know the period number and you know what kind of block that element is in, then you should be able to determine what the principal quantum number and the angular momentum quantum number is for that outermost electron. So for something like hydrogen, which is in period 1 and is an S block element, for S electrons, the principal quantum number would equal the period number, so n equals 1. And for the angular momentum number, well, for any S electron, L will always equal 0. Now take lithium, which is in period 2. Well, as an S block, the period number equals the quantum number, equals the principal quantum number. And since this is still going to be an S electron, the angular momentum number will once again equal 0. Going further across the same period as lithium is boron, which would be a p block element. As a p block element, just like s block elements, the principal quantum number of the outermost electron will equal the period number, so 2 in this case. However, the angular momentum number for any p electron will always equal 1. For something like sodium, which starts off the third period, well, it's an S block element. So the principal quantum number is going to equal the period number, 3. And as an S element, as an S electron, L will equal 0. For aluminum, which is also in period 3, in row 3 of the periodic table, but is a p block element, N will equal the period number, so in this case 3, and as a p block electron, that outermost electron is going to have an angular momentum number of 1. For calcium, which is in period 4 and is again an S block element, N is going to equal 4 because that's the period number, and L is going to equal 0 because we're talking about an S electron. Now copper is the fourth row of the periodic table. The fourth period is where we start seeing D block elements. Now, for a D block element, its outermost electron will have a principal quantum number that is 1 less than the period number. So 4 minus 1 would give us an N value of 3. Now, for any D block element, for any D electron, D will equal 2, always. Or L will equal 2, always for a D electron. In the case of krypton, which is now back in the P block of elements, its principal quantum number will be the same as the period number, which in this case is 4. And because it is a p electron, that outermost electron is a p electron, the angular momentum number is going to equal 1, because p electrons will always have a 1 quantum number. Now, going on to the third of the 4 quantum numbers would be the magnetic quantum number. This quantum number is important because it essentially tells you what subshell an electron is in, and each individual subshell is in fact an orbital, and the values that m can be range from positive to negative L. So let's look at the 4 main shells: S shell, P shell, D shell, and F shell. For S shell, L can equal 0. Therefore, that single shell, that single subshell in an S block element will always equal plus can range from plus or minus L. Well, if L equals 0, then plus or minus L is in fact 0. So for any s electron, it will always have a magnetic quantum number of 0. Now for a p block element, its outer electrons, for p electrons, the angular momentum number L equals 1. Therefore, the range of m values are from -1 to +1, which would essentially look like -1, 0, and then +1. For each individual, for those three different subshells, that would be their respective magnetic quantum number values. For D block electrons, the value of m in that case would range from -2 to +2, which would just look like this. The first subshell would be -2, followed by -1, 0, +1, and +2. And finally, for F block elements, their angular momentum number is always equal to 3, because that is one F set of orbitals would have for L. Now, since m ranges from positive to negative L, if L equals 3, then our range is going to be -3 to -2, -1, 0, +1, +2, and then +3. So there's a slide that basically has all those numbers saved for you guys if you look at the slides. Now, we just looked at the first three quantum numbers: principal, which tells you the energy level; the angular momentum quantum number, which tells you the sets or the shell that you're at, whether it's an S, P, D, or F shell. And now we just covered the magnetic quantum number, which tells you what specific subshell or what specific orbital in that set are you in. And this is just a groovy picture that shows the different shapes that the different individual orbitals can take. For the top left, we have an s orbital where the magnetic quantum number is always equal to 0. Therefore, that guy looks like a sphere. You only have one of those. For the p orbitals, where m can range from -1 to +1, that means that you have three distinct subshells or three distinct orbitals for any p shell. For d shells, they can have 5 distinct orbitals ranging from -2 to +2 for a value of m. And for F block, well, you're ranging from -3 to +3. That gives you 7 distinct orbitals. Now, cool. All that's fine and dandy. Now, there is one last quantum number, and that would be the electron spin, which is represented by m subscript s. Now, this essentially helps you distinguish this quality. Each orbital, each subshell, can hold up to 2 electrons. Therefore, if 2 electrons are in the same subshell or in the same orbital, they would have the same principal quantum number because they're at the same energy level. They would have the same angular momentum quantum number because they're in the same shell. And since they're in the same orbital, they would have the same magnetic quantum number. Therefore, since orbitals can hold up to 2 electrons, the electron spin is a value used to distinguish whether you're talking about the first electron in an orbital or the second electron in an orbital. And just by convention, the first electron that's used to fill an orbital or a subshell is given a value of +1/2 or spin up. And then for a second electron in a subshell is given a value of -1/2 for its electron spin, or a spin downwards. Now, for a set of subshells, taking something like p orbitals where there are 3 of them in a given shell, or d orbitals where there are 5 of them in a given shell. for a set of subshells, each individual subshell must have one electron in it before you start adding a second electron to any of those subshells. And that's just called Hund's rule. So now we're actually going to get into examples of filling subshells, filling orbitals. Now, at the bottom of the screen, I have what are the 1s orbitals. Effectively, the 1 comes from the principal quantum number, and then the s is simply the letter valuable of the angular momentum quantum number, where essentially if the angular momentum equals 0, then you're in an s block element. So, cool. We have, for something like hydrogen, we have only one electron to work with. And we can represent that with simply an arrow that is pointed straight upwards, and using that first and only electron to fill the 1s orbital. Now, we can assign that outermost electron a set of 4 quantum numbers. Because we are in the first period, and this is an s block element, the first period would equal the quantum number, the principal quantum number, so n equals 1. And with this being an s block electron, L would equal 0. And since m can range from positive to negative L, well, the only possible m value is 0. And since we are dealing with a electron that's in the upwards position, it would have a spin electron quantum number of positive 1/2. And that would essentially be the 4 quantum numbers to represent the outermost electron in hydrogen. Now for something like helium, helium has in fact 2 electrons that you can use to fill its orbitals. Now, we are still in the 1s orbital, therefore we can actually take that first electron and use it to fill that 1s orbital, but we still have one more electron left over, and that can be used to fill the remaining spot in this 1s orbital. Therefore, we have one electron that is spin up or spin 1/2, but the final electron, which is the one represented by a downwards arrow, it would have the following quantum numbers. N would equal 1, because any s block element, the principal quantum number equals the period number. Now L would equal 0, because any s block element, L will always equal 0. Now m will equal 0 because plus or minus L only gives you the value of 0. And then in this case, for that final electron that is pointed downwards, that has a downward spin, its magnetic spin would be represented by negative 1/2. Therefore, that would be how you represent the final electron for each of the elements in the first period. Moving on to the second period, we have lithium and beryllium. Now, lithium and beryllium, in the case of lithium, there are a total of 3 electrons you can work with. Now, this value is not simply the valence electrons, it's the valence and the internal electrons. Now, since there are 3 total electrons, and the only orbitals that we are working with are the 1s orbital and the 2s orbital, what we can do is essentially take those first 2 electrons and use them to fill the 1s orbital. So, like so. And then that third electron can be used to fill the 2s orbital. In the case of the outermost electron, the one that is occupying the 2s orbital for lithium, N would equal, since this is an s block element, n would equal the period number, which in this case is 2. L always equals 0 for an S block element. M equals can range from plus or minus 0, so 0 in this case. And then, since we have that final electron in the upwards position, its electron spin is going to actually be positive 1/2. Now let's look at beryllium. Beryllium has a total of 4 electrons, which includes the internal electrons and the outermost electrons. So since we have 4 electrons and we're only looking at the 1s and the 2s orbitals, we can use 2 of those 4 electrons to fill the 1s orbital, and then the remaining 2 electrons can be used to fill the 2s orbital. Now, for this final electron that is in that final electron occupying the 2s orbital in the downward spin position, it would have these following quantum numbers. As an s block element, n will equal the period number, which is 2 in this case. L would equal 0, m equals 0, and then to distinguish that second electron from the first electron, instead of having a positive 1/2 spin, it would have a negative 1/2 spin. And that's just to help give each electron its own set of quantum numbers. Now, further down the second period, we're actually going to enter the p block elements now. These could be boron, carbon, nitrogen, oxygen, fluorine, and neon. And for boron, we have a total of 5 electrons. So, 5 electrons. The first 2 can be used to fill the 1s orbital, and then the next 2 can be used to fill the 2s orbital. Now, for a p block element, you have to take into account that there are now 2 p orbitals, 2 being the quantum number, and p representing what set of orbitals we're in. Now, if we have a total of 5 electrons and we just use the 4 of them, that means we have 1 electron left over that we can in fact use to fill the first subshell of the 2p set of orbitals. To give that final electron that's occupying the first subshell, the first 2p subshell, the quantum numbers would be as followed. For any p electron, n would equal the period number, so 2. L will always equal 1 for any p electron. Now m can range from -1 to +1 in the case of a p electron. So the first subshell would have a value of -1, whereas the spin quantum number, since that final electron is pointed upwards, its spin is going to be positive 1/2. Now let's go to carbon, which is just one step further to the right of boron. Carbon has 6 total electrons you can work with, both internal and valence electrons. So let's just add those 6 electrons in. The first 2 can be used to fill the 1s orbital, and then the next 2 can be used to completely fill the 2s orbital. Now, for the 2p orbitals, we have to obey Hund's rule. We have 2 electrons left over, so effectively, we can use one of those leftover electrons to fill the first subshell, and then we can use that remaining electron to fill the second subshell. The reason why you do not actually make one arrow pointing up and one arrow pointed downwards in the first subshell is because each of these 3 subshells don't have 1 yet. Once they are all filled up, then you can start pairing electrons. Now for the set of quantum numbers to describe that final 2p electron, the one in the middle subshell, it would be as follows. For any p electron, the period number will give you the principal quantum number. For any period number, for any p electron, L will always equal 1. M can range from positive 1 to negative 1. So going from left to right, the first subshell would be negative 1. This middle subshell would be 0. And then, since that electron is still pointing upwards, its electron spin is going to be positive 1/2. Now we can go further down to nitrogen and oxygen, which these guys are cool. Nitrogen has a total of 7 electrons. However, if you can tell from the previous slide, it kind of gets pretty bulky and it will eventually get pretty cumbersome to keep including all the lower subshells. So in this case, I'm not including the 1s orbitals. They can just be assumed to be already filled, because you need to fill the lower ones first before you fill the higher energetic ones. So in this case, we're just going to be looking at the valence electrons. So kind of combining, using the group number again. For nitrogen, nitrogen is in group 15, so it has a total of 5 valence electrons. Now, those first 2 electrons are going to be used to fill the 2s orbital, one that's going upwards and one that's going downwards. Now, for the remaining 3 electrons, those are going to be used to fill the 2p orbitals, and in this case, you are going to have 1 for each subshell. Since nitrogen has 5 valence electrons and we're only thinking about the shells of the outer electrons, we have now used up all our electrons. Now to assign that final electron its 4 sets of quantum numbers, pretty straightforward again since we're dealing with a p block element. And it's going to equal the period number, which is 2. L will equal 1 for any p element, and M will equal, for this final guy, positive 1. Since M can range from negative to positive L, the first subshell of P of 2P would be negative 1, then 0. Now we're at positive 1. And our final electron is still pointed upwards, so it will in fact have a positive 1/2 spin. Now, going on to something like oxygen. For oxygen, we are going to be dealing with 6 valence electrons, so its outermost shell is going to look more like this. The first 2 of those 6 valence electrons are going to be used to fill the 2s orbital, and then the remaining 4 are going to be used to fill the subshells of the 2p orbitals. Now, what I've done here is that I have used 5 of my 6 valence electrons, and there is still 1 more electron. However, since each of the 2p subshells have been filled, now I can start pairing electrons. So that final electron, that 6th one, is going to be used to form a spin down electron. So, to describe the 4 quantum numbers for that final electron, the one that is in the first subshell of the 2p orbitals but is spin downwards, it would have the following quantum numbers. 2, the period number, L equaling 1 because this is a p electron, M equaling negative 1 because it is in the first subshell, and then since it is spin downwards, its value is going to be negative 1/2. Now this leaves us 2 more p block elements, which would be fluorine and neon. In the case of fluorine, it's in group 17, so we have 7 valence electrons to think about. And, well, the very first 2 can be used to fill the 2s orbital, and then we are going to have 5 remaining. So effectively, we are going to use 3 of those 5 to first fill each 2p subshell. Then, once each subshell is filled, only then will we start pairing up electrons. So, if fluorine has 7 valence electrons and we have just used 5, and each 2p subshell is filled, now we can start pairing off those remaining electrons. Therefore, the representing those electrons in their shell notation would be like so for fluorine. To give the quantum numbers for the final electron in fluorine, which is in the middle 2p subshell, but pointed downwards, its quantum numbers are going to be 2 for the period number. It will be 1 since we are dealing with a p block element. It would be 0 because that is the middle subshell. And then m sub s, since our electrons point downwards, is going to be -1/2. Neon, we have now finally reached a noble gas, and we are going to essentially use its 8 valence electrons to fill the 2s and 2p subshell. So, just to kind of cheat a bit, let's say we basically filled up all the electrons just like we did with fluorine. However, this only accounts for 7 of those 8 valence electrons. We still have 1 remaining electron, and that last electron can be used to fill the final 2p subshell, or the final 2p orbital. And describing the quantum number, the set of quantum numbers for that final electron would be 2 for the period number. Any p block element is always going to have a 1 for the angular momentum. Since this is in the third subshell, and the values of m can range from -1, 0, and +1. In this case, in the final subshell, that the angular momentum or the magnetic number is going to be +1. And since it is spin downwards, it's going to have a value of -1/2. Now, in the case of the third period of elements, it's just like the second period. Basically, we haven't reached any new blocks of elements, so effectively the same process. The S block elements would be sodium and magnesium. The P blocks would be aluminum, silicon, phosphorus, sulfur, chlorine, and argon. Now, for the case of magnesium, there are 2 valence electrons, and those 2 valence electrons would be used to fill the 3s. The 3s shell, the 3s orbital. 3 coming from the principal quantum number, and s being the type of block or the type of shell we're at. Now in this case, for that final electron that's pointed spin down for 3s, magnesium, its set of quantum numbers would be n equals 3, L equals 0, M equals 0, and M sub s equals -1/2. Now going further to the right, for say chlorine, which is in group 17, period 3, well, it would have 7 valence electrons to work with. The first 2 would fill the 3s orbital, and then for the set of 3p orbitals, 3 electrons would be used to fill each subshell, and then the 2 remaining would be paired off in the first 2 subshells. Therefore, the final electron in chlorine, which is in the middle 2p orbital, its principal quantum number would be 3, angular momentum as a p block element would be 1, m would be +1, would actually in fact be, m would actually be 0, because that is the middle shell, and then m sub s would be positive would be negative 1/2. M sub s would be negative 1/2 because that final electron in the middle subshell is spin downwards. Now, period 4 is where we start to see a new block of elements, namely the transition metals or the d block elements. And just taking into account the valence electrons, we can look at it this way. The actual orbitals that we have to fill for a period 4 element are going to be the 4s orbital, again the 4p orbitals if we get far enough. However, in the center is going to be the 3d orbitals, the 3 being the principal quantum number. For a d block element, n would equal the period number minus 1, so 4 minus 1 equals 3. Now let's look at potassium, which is the very first element in the 4th period. It's an s block element. Therefore, we have 1 electron to work with, and that very first electron is going to be used to fill the 4s orbital. And its quantum numbers are going to be, well, the period is 4, and this is an s element, so n equals the period number. Any s electron is going to equal 0 for the angular momentum, which means that the only possible value of the magnetic quantum number is also going to be 0. And we're dealing with an upward spin, therefore that's going to be a positive 1/2 electron. Let's skip ahead to a d block element for, say, vanadium, which effectively goes, so the d block in the 4th period starts with scantium, titanium, then vanadium. So that's going to be 3 d electrons in plus the first 2 from the 4s. So effectively, we have 5 electrons to work with. Now, that very first electron, as always, you fill the s orbital first, and then that second electron would be spin downwards for the 4s orbital. Now, since vanadium is 3 elements into the d block elements, we have 3 electrons to use to fill the d block. So, however, we have 5 distinct subshells. Therefore, we are going to use those 3 remaining electrons to fill up separate subshells. Since according to Hund's rule, we do not pair off electrons up and down until each subshell is filled. Now, to describe the 4 quantum numbers for that final 3d electron, well, for any d electron, the principal quantum number is going to be the period number minus 1. For period minus 1 would be 3. L is going to equal 2, since L equals 0 for an s-type electron, L equals 1 for a p electron, and L equals 2 always for a d electron. Now, M can range from positive to negative L, which means these subshells are going to range from -2 to +2. And just going from left to right, it's going to be -2, -1, 0. So that final electron is going to have a magnetic quantum number of 0. And since it is still spin upwards, it is going to have a positive 1/2 for its electron spin. That would be the 4 quantum numbers for vanadium. Going even further into the period 4 d block elements would be cobalt. Now, if we count up cobalt, it is essentially 1, 2, 3, 4, 5, 6, 7 d elements into the d block. So that means that we have 7 d electrons as well as the 2 s electrons. So a total of 9 electrons to think about. The first 2 are going to be used to fill the 4s orbital, always. And now we're going to start filling up those remaining 7 d electrons. We're going to use those to fill the d subshells, or the d orbitals. And essentially, we're going to fill each subshell with 1 first. Cool. Now, I just used 5 electrons, 5d electrons. Cobalt is 7 elements deep into the d block, therefore there are a total of 7 d electrons. We just used 5 of them, therefore there are 2 left over, and since each subshell is now filled, we can now start pairing off electrons, which is what we're going to do for the final 2. Therefore, to describe the 4 quantum numbers for this final electron in the d orbitals, the one that is pointed downwards in the second subshell, well, principal quantum numbers could equal 3 because 4 minus 1 is 3. L for any d block for any d electron is going to be 2. Now, going from left to right, the first d subshell will be -2. Our final electron is in the second subshell, so its values could be -1. And then the spin, since the spin is downwards, its electron spin quantum number is going to in fact be -1/2. Now going on to zinc, zinc is all the way in the final slot of the d block, or it's 10 elements into the d block of elements. So that means that we have 10 d electrons as well as the first 2 4s electrons. So just going to fill up the 4s electrons first, like so. And now we have d electrons. So we have 10 in total, and I'm just going to cheat a bit. I know that there are 5 subshells, which means that each is going to get its own pair of electrons, because 10 divided by 2 is 5. Now, to describe that final electron, which is this guy all the way to the right, which is in the rightmost subshell and pointed downwards, we would describe its 4 quantum numbers as, for a d element, the principal quantum number is 1 less than the period number, in this case 3. Angular momentum will always equal 2 for any d electron. M can range from -2 to +2, therefore from left to right, the subshells go -2, -1, 0, +1, +2. Therefore that final electron is going to have a magnetic quantum number of +2. And since it is spin down, it will have a -1/2 electron spin. Now, one last example, thank goodness, is going to be, let's use arsenic. Arsenic is in the same period, it's in the 4th period, and it is 3 electrons, it is 3 elements into the 4th p block. So there will be 3 p electrons. We have the first 10 electrons from the 3d set of elements that we just passed, and we also have those 2 4s electrons. So essentially, since we are in the p block, we effectively went through the 4s and each of the 3d electron orbitals. Which means that basically the 4s and the 3d shells are completely filled. Now, since arsenic is 3 elements into the p block, that means that we have 3 electrons, 3 p electrons to work with. And there are 3 subshells. Therefore, each subshell is going to get its own unpaired electron. Therefore, the final electron, the one that is in the last subshell of the 4p orbitals, it would have this following quantum numbers. since we're now in a p electron, the period number will equal the principal quantum number, which in this case is 4. L for any p electron will always equal 1. M can range from -1 to +1. Therefore, that final spot would have a +1 as a magnetic quantum number. And since it is spin upwards, the quantum number for the electron spin is going to be +1/2. Oh boy. Alright guys, so essentially that is it for this week's lecture material on representing the electrons in, or at the very least representing the valence electrons according to orbitals. Now, as far as extra credit, this will be due by end of day Saturday this week, the 28th. Essentially what I want you to do is assign the valence electrons into their appropriate orbitals for rubidium, technetium, and tellurium. So these guys are in period 5. So think about 5s, 4d, and 5p. What I mean by assign the valence electrons, don't do the 1s, then the 2s, then the 2p, then the 3s, 3p. Don't build up. Just go with the final set. So essentially, the 4s electrons, the 5s electrons, the 4d electrons, and then the 5p electrons. And then also, as part of the extra credit, I want you for rubidium, technetium, and tellurium, that final electron, tell me what the 4 quantum numbers are for that final electron. Ooh, man. Now, just as far as lectures go, since we are now online, I'm going to be condensing lecture to just one video, which for you guys, it doesn't change anything since we only met once a week anyways. Today we just did the quantum mechanical model. Next week we'll get into molecular orbital theory, and then the Monday after, 2 Mondays from now, you will get access to your formal extra credit, which is essentially a practice exam, and then your third exam. You'll get access to that on April 6th, but it will not be due until April 17th. So 2 Fridays after the due date, or 2 Fridays after the opening date. And then afterwards we'll do liquids and vapor pressure, solution composition, and then finally the Thursday, the Thursday right after your final lecture is going to be when you will have access to your last exam. We don't have final exams. I'm not into them. So essentially your 4th exam will be made available to you that Thursday after our last lecture. And it will not be due until the last day of the semester before final exams, or Friday, May 8th. Just have it into me by at least 11:59. And then one last thing to cover is that administration has changed up some things. And that is that midterm grades are now pushed back to Friday, April 10th. Doesn't really matter to anyone, doesn't change anything. But what may matter is that the last day to drop or withdraw from classes without being negatively impacted with a failing grade has now been pushed back to April 24th. Now, that's basically, what does that mean? That means that by April 24th, you will have already had your 3rd exam and received the grade for it. And you will already have most of the lecture material for the 4th exam. Therefore, before the last day to drop, you will already know where you stand and most of what you need to know going into the 4th exam. Therefore, if this online format is not working out, well, you will know, you will have a good understanding where you stand by then. Now, guys, that is essentially the lecture material for this week on the quantum mechanical model. As always, I do enjoy teaching you guys, and well, I'm done. You guys enjoy your week.